Hello everyone, so in this video I have categorized previous year's JEE Mains questions from the chapter Current Electricity into problem type. Now after watching this video till very end you have the idea what different types of problems can be asked in JEE Mains. So let's see how we're going to proceed. Right, so first we'll discuss the weightage and then the syllabus, then mind maps where I have mentioned different topics and topic from this chapter, and then we will discuss previous year's questions for JEE Mains, which I have categorized as problem types. Right, and who will get benefited from this video? If you have basic knowledge but you are unable to approach problems, you're facing difficulty in numericals, then this video is for you. And you have basic NCERT level knowledge but you want to write JEE Mains exam but you are struggling with the problems numerical part, so this video is for you. And you have done some coaching, still your problem solving is not up to the mark, so this video is for you. And how you can use this video effectively? So first of all you have to revise whatever short notes that you have prepared for current electricity, and then while watching the video write down the important information you come across, and then whenever I discuss an illustration, pause the video, try to solve the question on your own. If you're not able to solve the question, then you can see the solution. Right, so first let us see the weightage. Around 2 to 3 questions can be asked from this chapter, so it's a high priority topic, so you must master this topic, right? And this is the syllabus, and as per the last year's syllabus there is no change, it is same syllabus. And this is the mind map where I have mentioned different topics and subtopics from this chapter. You can pause the video and just have a look at it. Right, now let us see the very first problem type, and it is based on the concept of current, and usually we define current as instantaneous and average current. So we'll see different illustrations so that you have the idea what I'm talking about. So first illustration is the electric current through a wire varies with time as I equals to I naught plus beta times t, where I naught is 20 ampere and beta is 3 ampere per second. The amount of electric charge crossed through the section of the wire in 20 seconds. So we have to find the charge. And if you remember, current is defined as dq by dt, the rate of change of charge. And here we have given I. So if I write this I, so we have given I as I naught is 20, beta is 3 times t. So if I write I as dq by dt, so this can be written as dq equals to 20 plus 3t times dt. And we have to find the amount of charge that has flown through the conductor in 20 seconds. So what you can do, you can integrate this. If you integrate this, you will get the charge. So the interval will be 0 to 20 seconds. So the integration of 20 plus 3t will be 20t plus 3t square by 2. Now let us put the limit from 0 to 20 seconds. So it comes out to be 400 plus 3 by 2 times 400. So this will be 200 and this comes out to be 6, so this will be 1000, right? So 1000 coulomb. So option 2 is the right answer. Right, so now you know, like if we have to find the charge, we have to do the integration, right? If I is given as a function of time. Let us see next illustration. The current in a conductor is expressed as I equals to 3t square plus 4t cube, where I is in amperes, t is in seconds. The amount of charge that flown through the section of the conductor during 1 to 2 seconds. Again the same question, you can integrate. So 3t square plus 4t cube, and time is varying from 1 to 2 seconds. So by using this, you'll be able to get the answer. Right, let us see next question, next problem type, and it is based on current density. Let us see. The current density in a cylinder varies. A wire of radius r, which is 4 millimeter, is 10 raised to power 6 ampere per meter square. The current through the outer portion of the wire between the radial distance r by 2 and r is x times pi ampere, where x is. Now here we have to find the current by using the current density formula, right? So current density in case of a uniform distribution of the current throughout the cross section is defined as current per unit area, right? And if you want to find the current through this, let me just draw the cross section. So we have given a circular cross section, radius is given as r, and we have to find the current which is flowing through this cross section from r by 2 to r. So this is r by 2. So in this region we have to find the current, and current density is uniform. So what you have to do, you have to multiply, so to find the current you have to multiply current density with the desired area. So in this case the area of this shaded area we have to consider. Now what is this shaded area? Let me so it is nothing but the area of a big circle minus area of the small circle. So it will be pi r square minus pi r square by 4. So that will be 3 by 4 pi r square. So current density is 10 raised to power 6. Area is 3 by 4 pi r. Radius is given as 4 millimeters. So let us convert radius into SI units. So this will be 4 into 10 raised to power minus 3 meters. So 4 into 10 raised to power minus 3 square. So this comes out to be 3 by 4 times 16 times 10 raised to power 6 minus 6 times pi. So this will give us 4, and it comes out to be 12 pi. So and this is given as x times pi. So x is 12. So 12 is the answer of this question. Okay, next problem type is based on drift velocity. So what are the formulas that you have to remember in case of drift velocity? So Vd is given as J upon Ne, where J is the current density, or it can be written as I upon NEA, or you can remember drift velocity is minus E capital E tau by M, where capital E is the electric field inside the conductor, tau is the average relaxation time, and M is the mass of the charge carrier, E is the charge on the carrier. So let us see a question. The number density of free electrons in copper is nearly 8 into 10 raised to power 28 per meter cube. So number density is number of charge carriers per unit volume. So N is 8 into 10 raised to power 28 per meter cube. A copper wire has its area of cross section 2 into 10 raised to power minus 6. So area of cross section is given as 2 into 10 raised to power minus 6 square meter, and is carrying a current of 3.2 ampere. So current is given as 3.2 ampere, and we have to find the drift velocity or drift speed of the electron okay, in the order of 10 raised to power minus 6, let us say. So Vd is nothing but J upon Ne, or we can write this as I upon NEA. I is given, A is given, N is given, right? Let us put the values. So current is 3.2. Number density is 8 into 10 raised to power 28. And 1.6 into 10 raised to power minus 19 is the charge on one electron. Times area is given as 2 into 10 raised to power minus 6. So let us simplify this. So this will give us 0.4, this will give us 4. So we have 1 by 8 into 10 raised to power minus 28 plus 25. So this can be written as 0.125 into 10 raised to power minus 3. And we have to find the drift speed of the order in terms of micrometer per second. So that can be written as 125 into 10 raised to power minus 6 meters per second. So if you look at the question, we have to fill the blank, which is 125. So 125 is the answer of this question. Right, let us see next question. A current of 2 ampere flows through the wire of cross-sectional area to 25 square millimeter. The number of free electrons in the cubic meter is 2 into 10 raised to power 28. Basically, this is given as number density or number of charge carriers per unit volume. The drift velocity of the electron. Again, same question based on the same concept. We have to use Vd as I upon NEA. Area is given, current is given, number density is given. So by substituting the values, we'll get the answer. The answer is 25 in this particular case. Right, so now let us see the next problem type, and it is based on temperature dependence of resistance. So as we increase the temperature of the conductor, its resistance increases. But in case of semiconductor, as we increase the temperature, the conductivity increases. So let us see some illustration based on the same concept. Right, so here to measure the temperature coefficient of resistivity alpha of a semiconductor, an electrical arrangement shown in the figure is prepared. Now the arm BC is made up of a semiconductor. So arm BC, this is semiconductor. The experiment is being conducted at 25 degrees Celsius, and the resistance of the semiconductor arm is 3 milliohms. An arm BC is cooled at a constant rate of 2 degree Celsius per second. If the galvanometer G shows no deflection after 10 seconds, then alpha is. So when there is no deflection in the galvanometer, this arrangement will behave as a balanced Wheatstone bridge. And we know that in case of a balanced Wheatstone bridge, if this is R1 and this is R2 and this is R3 and this is R4, so when we have balanced Wheatstone bridge, R1 by R2 is equals to R3 by R4. So after 10 seconds, the temperature has decreased by how much amount? 20 degrees Celsius, right? Because in 1 second we are decreasing temperature by 2 degrees Celsius, so in 10 seconds it will decrease to 20 degrees Celsius. And what is the resistance at the new temperature? Let us find the resistance of this branch BC at new temperature. R1 is 0.8 milliohms, R2 is 1 milliohms, and resistance of branch BC divided by resistance of DC, which is 3 milliampere, so 3 milliohms. So this comes out to be how much? So 4 by 5 times 3 milliohms, which is 2.4 milliohms. That is the resistance of the semiconductor at new temperature. Now if we apply the concept of temperature dependence of resistance, so we can say, and they're talking about the temperature coefficient of resistivity. And if I assume that we are not changing the dimension, then the resistance will be directly proportional to the resistivity, because R is equals to rho L by A. So if we are ignoring any change in the dimension, we can say R will be proportional to rho. So we can say the change in the resistance. So R is the resistance at new temperature time is equals to resistance at old temperature times 1 plus alpha times the change in temperature. So change in temperature will be minus 20. Okay, so let us put the value. So 2.4 milli divided by old value is 3 milli minus 1 equals to minus 20 alpha. So this comes out to be 4 by 5. So minus 1 by 5 multiplied with minus 20, right? So from this alpha value comes out to be 1 upon 100, and this will be, and since we are cooling, since we are decreasing the temperature, so let me also put a negative sign here, right? Because as we decrease the temperature, the resistance will decrease, so there has to be a negative sign here, right? So this will become positive and we'll get a negative here, right? So this will be 1 into 10 raised per minus 2 per degree Celsius. Got it? So the option 3 is the right answer. We have given a resistance of the wire at different temperatures. At 0 degrees Celsius, 100 degrees Celsius, and 80 degrees Celsius, the resistances are 10, 10.2, and 10.95 ohms respectively. The temperature T in Kelvin scale. Okay, so what we can say, resistance at a particular temperature is equal to resistance at 0 degrees Celsius times 1 plus alpha times theta. So we can use this formula. So if we apply this formula at 100 degrees Celsius and at T degrees Celsius, let us see. So at 100 degrees Celsius, the value is 10.2, and this is 10, 1 plus alpha times 100. So this can be written as 1.02 minus 1 by 100. So that is alpha. So alpha will be 2 into 10 raised power minus 4 per degree Celsius. Now we can use this value of alpha while taking T temperature as T degree Celsius. So temperature at T, if I take temperature at T degree Celsius, then the resistance will be 10.95. Resistance at 0 degree Celsius is 10. 1 plus alpha is 2 into 10 raised power minus 4 times the change in temperature. So from 0 to T. So that will be T. So this comes out to be 1.095 minus 1. So that will be 0.095 divided by 2 into 10 raised to power 4. So this comes out to be 950 by 2, which will be 475 degrees Celsius. Now we have to find temperature in Kelvin. So 475 plus 273. So this will give us 748 Kelvin. So T in Kelvin is 748. So that is the answer. Right. So now let's see another illustration. An electric toaster has a resistance of 60 ohms at room temperature, which is 27 degrees Celsius, and the toaster is connected to 220 volt supply. If the current flowing through it reaches 2.75, so what happens in this case? As the current passes through the toaster, due to the joules heating, the temperature will increase, and as the temperature increases, the resistance will also increase. As the resistance increases, the current which is flowing through the toaster will decrease. So let us see what is the initial current. So let us see the corresponding resistance. So if we have I is equals to V by R, I is given as 2.75, V is 220. From this we can find the value of new resistance. So R comes out to be 220 upon 2.75, so which will be 44, and this will be 0.55, so it will be 4 upon 0.05, so it comes out to be 80 ohms. So the resistance has increased from 60 to 80. So what we can do, we can write resistance at new temperature. So basically we have to find the temperature attained. So what we can do, we can say temperature at say theta is equals to resistance at 27 degrees Celsius 1 plus a temperature coefficient, which is given as 2 into 10 raised to power minus 4 times theta minus 27. Okay, so change in the temperature. Let us put the values. So resistance at new temperature is 80. So 80 is equals to 60 times 1 plus 2 into 10 raised to power minus 4 theta minus 27. So this will give us 4 by 3 minus 1 equals to 2 into 10 raised to power minus 4 theta minus 27, and this comes out to be 1 by 6 times 10 raised to power 4 plus 27. So which will be 1667 plus 27 approximately, and it comes out to be 1694 degrees Celsius. So that is the temperature of the toaster, right? So option 3 is the right answer. Right, so now let us see the next problem type, and it is based on the formula of resistance, the relation between resistance and the resistivity. So R is equals to rho L by A, where rho is the resistivity or specific resistance, L is the length of the conductor, A is the area of cross section, and R is the resistance. So let us see this question. The length of the metallic wire is increased by 20% and its area of cross section is reduced by 4%. The percentage change in the resistance of the metallic wire. So R is rho L by A, and resistivity depends upon the material. If we are not changing the material at a particular temperature, there will be no change in the resistivity. but if we change the dimension, the resistance will change. So length has increased by 20%, so L plus 20% of L, which is nothing but 1.2 times L, and the area of cross section has reduced by 4%, so A minus 4% of A, so that will be 0.96 of A. Now the new resistance will be rho times 1.2 L upon 0.96 A, which comes out to be 1.25 rho L by A. Now this rho L by A is the new original resistance. Let me call this as R naught. So 1.25 times R naught. So if you do these changes, then the resistance will become 1.2 times the original value. And if you want to find the percentage change, so percentage change in the resistance will be given as change divided by the original value multiplied with the 100. So change will be 1.25 minus 1 times R naught, and the original is R naught times 100. So this comes out to be 25%. Right, so let us see the next illustration. A wire of resistance 160 ohms is melted and drawn into a wire of 1/4 of its length. So we have given, say, a conductor, a wire, and now we have decreased the length. So we have recasted it into a wire of 1/4 of the length. So if this is L, when we recast this, and we'll in such kind of a question, we'll assume volume doesn't change. So as we recast it into a smaller length, the area of cross section will increase for same volume. So as we recast, it will look like this, right? That is the new area, and this length will become L by 4. Got it? So here, let me just give you a trick. So if we are changing the length by recasting or by drawing or by compressing, then resistance will be directly proportional to the square of the length, or we can say resistance will be inversely proportional to square of the area. So this you have to remember. So here we are changing the length, so we can say the new R2 by R1. R2 is the new resistance, R1 is the original resistance, will be equals to L2 square by L1 square. L2 is the new length, L1 is the original length. So L2 is 1/4 of the original, so L1 by 4 square upon L1 square, so that comes out to be 1 by 16. So R2 will become 1/16 of the original value, and the original resistance is 160. So this comes out to be 10 ohms. So option 1 is the right answer. Two wires A and B are made up of the same material and have same mass. So mass are same, and they are made of the same material. If the material is same, we can say they must be having same density, same resistivity. So these are material property. Wire A has a radius of 2 millimeters and wire B has a radius of 4 millimeters. So this radius is the radius of the cross section, and the resistance of wire B is 2 ohms. When we have to find the resistance of wire A, so let us see what we can do. So resistivity, so I'm showing, I'm taking density as sigma and resistivity as rho. So density is mass upon volume, and volume for a cylinder is area of cross section times the length. So L times pi r square. Now here density is same for both the wires, mass is same for both the wire, pi is constant. So we can say length will be inversely proportional to square of the radius. So resistance will be rho L by A. Now resistivity is same for both the wire and area, and this will be rho L upon pi r square. So we can say resistance will be proportional to L upon r square, and L is proportional to 1 by r square, so we can say it is proportional to 1 upon r raised to power 4. Now we have the relation between resistance and the radius of the cross section. So we can say R2 by R1 will be equals to R1 by R2 raised to power 4. So now let us substitute the values. So we have to find R2. 2 stands for, you can say, we have to find the resistance of wire A now. So let us take two for wire A and one for wire B. So R2 by R1, R1 will be 2 ohms, which is given in the question. Then R1 for wire B is 4, and for wire A it is 2. So this comes out to 2 raised to power 4. So R2 comes out to be 2 into 16, which is 32 ohms. So 32 ohms is the answer. So whenever you get such kind of a question, it is always recommended to form a proportionality relation and use the ratios. Okay, right. Let us see the next question. A wire of resistance capital R and radius small r is stretched till its radius becomes r by 2, and if the new resistance of the stretched wire is x times r, then the value of x. So I told you, whenever we are stretching a wire or we are recasting a wire, resistance will be directly proportional to L square, or resistance will be inversely proportional to square of the area of cross section, and area of cross section is directly proportional to square of the radius of the cross section. So we can say resistance will be inversely proportional to R raised to power 4. So we got the proportionality. So R2 by R1 will be equals to R1 by R2 raised to power 4. So here R1 is given as R, and so R1 is small r and R2 will be R by 2, and R1 is capital R. So let us find R2. Capital R, R1 is R by 2 raised to power 4. So this comes out to be 16 times capital R. So X is 16. Okay, let us see the next problem type, and it is based on equivalent resistance. So we'll be giving a circuit, and we have to find the equivalent resistance between any 2 points. So let us see this question. The value of an unknown resistance X for which the potential difference between B and D will be 0 in the arrangement. So potential difference between B and D, or you can say the potential of point B and D are equal. Right, so let us see. So potential of B and D to be same, what we can say, we'll get an arrangement of balanced Wheatstone bridge if the potential of B and D are equal. So the resistance of this combination and the resistance of this combination, the ratio of these two, let me call this as R1 and this is a R2, and this resistance as R3 and this as R4. When VB is equals to VD, then R1 by R2 will be equals to R3 by R4. Now let us find R1, R2, R3 and R4. So R1 is what? So we have 12 and 12 in series, so that will become 24. Now this 24 is in parallel with this 24, so it will become 12. So R1 is 12 ohms. Now if you look at R2, so we have 12 and 12 in parallel, and this combination is in series with X. So R2 will be X plus 6 ohms. Now if you look at R3, 1 and 1 are in parallel, so R3 will be equals to 0.5 ohms and R4 is 0.5 ohms. So it means this ratio should be 1, right? So 12 upon X plus 6 should be equals to 1. So X X plus 6, so this comes out to be 0.5 and this will be 0.5. Yeah, so this comes out to be 6 ohms. So option 4 is the right answer. Let us see next question. Now we have to find the equivalent resistance of the following network. So whenever we have lots of resistors, first of all you have to figure out what resistors are in series and which resistors are in parallel, or is there any short circuiting in one of the resistors. So if you consider in this case, if you consider 6 ohms, the ends of this 6 ohms are connected with a connecting wire, so it means it is short circuited, so the potential of this point will be same as potential of this point. So we can remove this resistor. right? So if I show this the circuit, it will look like this. So we have 2 ohms, here we have 2 ohms, this is 2 ohms, and this 3 are in parallel, so I can show it with a single resistor of 3 by 2. Now if you look at this 2 ohms and this 2 ohms, they are in parallel because their ends are joined together, so this will become 1. So we have 1, 2, 1.5, this is A and this is B. Now this 2 and this 1 are in series, so we have 3, here we have 1.5 A, B. Now 3 and 1.5 are in parallel, so 3 times 1.5 upon 3 plus 1.5, so that will be 4.5 upon 4.5. So this comes out to be 1. So that is the equivalent resistance between A and B. So 1 is the answer of this question. So here we have to find the equivalent resistance between A and B. So this circuit is given to us. So first step would be we have to identify the series and the parallel combination. So if you look at these 10 and 5, they are in series. This 7 and 8, they are in series, and 4 and 11, they are in series. So it will be 15 ohms, this is 15 ohms, and this is 15 ohms. Right, so now we have to see the parallel combination. Now let us see a trick. I'm going to mark equipotential points. Let us take this point as 1. So this point is also 1 because they are connected with a connecting wire. If I take this point as 2, this point will be 2. And this is A and this is B. Now let me show all these equipotential points. So this is A, 1, 2, B. Now I'm going to show connect the resistors between these points. So between A and 1, we have only one resistor, 6 ohms. So this will be 6 ohms. And between 1 and 2, so this 15 is between 1 and 2, this 15 is between 1 and 2, this 15 is also between 1 and 2. So we can say there are 3 resistors connected in parallel, 15 ohms, 15 ohms, and 15 ohms. And between 2 and B, we have 8 ohms. Now let us simplify this. So this 15 are in parallel, so this will become 5 ohms. Now this 5 ohms, 6 ohms, and 8 ohms are in series. So 6 plus 5 plus 8, so that comes out to be 19 ohms. So option 2 is the right answer. Right, so let us see the next illustration. The effective resistance between A and B, if the resistance of each resistor is R, will be. Now if you look at this diagram, it is quite symmetrical. All resistors are identical, and in this case, this is the axis of symmetry, right? So this is the axis, and so it means this point and this point, these 2 points will be equipotential, right? If this point is 1, this point is also 1, they will be having the same potential. Even this point will be having the same potential, right? If they have same potential, then there will be no resistance in this resistor and no resistance. So there will be no current in this resistor and there will be no current in this resistor. So we can remove these 2 resistors. So, and we can redraw the diagram. So we can remove those 2 resistors. Now the circuit has simplified a bit. So we have R and R in series, this R and this R are in series, and this R and this R are in series. This is R, this is R. This point is A, this point is B. So if we consider these 6 resistors, so 3 2Rs in parallel, so that will become 2R by 3. And this R 2R by 3 and R in series, so R plus 2R by 3 plus R, so they are in series, so it will be 8R by 3. So option 1 is the right answer. Let us see this question. 3 voltmeters all having different internal resistances, so they have different resistances, are joined as shown in the figure. with some potential differences applied across A and B. So there will be some current flowing. So whatever current which is entering A should also leave B. When some potential difference is applied across A and B, the reading of the voltmeters are V1, V2 and V3 respectively. Choose the correct option. So we have to compare the voltages. So one thing we can say, the potential drop across these two voltmeters should be equals to the potential drop across this voltmeter, because they are connected in parallel. So we can say V1 plus V2 should be equals to V3. So option 4 is the right answer. Got it? Because V1 and V2 have same current. Their potential is not same. But we know that between these 2 points and between these 2 points, the potential difference is same. Okay? So option 4 is the right answer. Let us see this question. A potential divider circuit is shown in the figure, the output voltage. So we have to find the voltage across these 5 resistors. So what we can do in this case, so if we assume, say, some current I. So what is this current? So if you consider this loop, so current will be voltage divided by the total resistance. So it will be 3.3 into 10 raised to power 3 plus 1, 2, 3, 4, 5, 6, 7. So that will be 0.7 times 10 raised to power 3. So which comes out to be 4 divided by 4 into 10 raised to power 3. It will be 10 raised to power minus 3 ampere. So we got the current. So what is the voltage across these 5 resistors? Let me call this as V naught. It will be I times R, and current is 10 raised to power minus 3, and the resistance of these 5 resistors which are in series will be 500. So it comes out to be 0.5 volts. So option 3 is the right answer. Now let us see the next problem type, and it is based on the equivalent conductivity. So here we are going to connect two conductors together, and then we have to find the equivalent conductivity. So two metallic wires of identical dimensions are connected in series. So let us say we have two cylindrical conductors of identical dimension. This is A, length of one of the conductor is L, and the first conductor has a conductivity sigma 1, and for the second it is sigma 2. The effective conductivity. So now we're going to replace these two wires with a single wire of same dimension. Its length is 2L, and the area of cross section is A, and the conductivity is sigma. So if they are identical, we can say their resistance should also be same. So what is R1? So R1 will be 1 upon sigma 1 times L by A plus 1 upon sigma 2 times L by A, because these two conductors are connected in series. And for the second case, R2 comes out to be 1 upon sigma times 2L by A. Okay, so if this is the equivalent combination for these two in series, then we can say R2 should be equals to R1. So 1 L by A times 2 by sigma should be equals to L by A times 1 by sigma 1 plus 1 by sigma 2. So L by A will get cancelled out. So from this, sigma comes out to be sigma 1 sigma 2 times 2 divided by sigma 1 plus sigma 2. So option B is the right answer. Now let us see the next problem type, and it is based on wire cutting and then rejoining the wires, right? And again it is based on the series and parallel combination. Let us see. A wire of resistance R and length L is cut into 5 parts. Now we have given a wire, and now we are cutting this wire into 5 parts. So if the total resistance is R, then for each part the resistance will become 1/5. So R by 5, R by 5, R by 5, R by 5. If these parts are joined in parallel, so when we connect them in parallel, then the equivalent resistance will be what? It will be resistance of one of the part divided by the number of parts in parallel. So it will be R by 25. So option 1 is the right answer. Let us see next illustration. A wire of resistance 20 ohms is divided into 10 equal parts and resulting pairs. Okay, a combination of two parts are connected in parallel and so on. Now the resulting pairs of parallel combinations are connected in series. Now we have 10 parts. Now we are taking two parts at a time and joining them in parallel. Something like this. Right? It's like this. This is the combination. And how many combinations will be there? How many resistors will be there? So there will be 5. So this will be, so 10 parts. So the resistance of each part will be 20 by 10. So it will be 2 ohms. So this is 2 ohms. This is 2 ohms, right? 2 ohms, 2 ohms. So the resistance of one part will be 1 ohm, right? Now how many sub blocks, some small blocks we have? 5. So it will be 1 into 5. So that will be 5 ohms. So answer will be 5 in this case. Now let us see the combination of cells. The reading in the ideal voltmeter V shown in the given circuit diagram is, so we have to find the reading of this voltmeter, and it is connected across a real battery which is having an EMF 5 volt and the resistance, internal resistance 0.2 ohms. And if you look at the left circuit, all these batteries are connected in series and they have the same polarity. So negative, positive, negative, positive, negative, positive, right? Negative, positive, negative, positive, negative, positive, negative, positive. So if you look at this, so these are in same polarity. So the E equivalent in this case will be sum of all the EMFs. So how many cells we have? Identical cells we have 7. So 7 times 0.2. So it will be 1.4 volts. And R equivalent is nothing but the sum of all the internal resistances. So it will be 7 times, sorry, this says EMF is 5. It is not 0.2. Let me correct this. EMF is 5. So that will become 35. And resistance is 0.2. So it will be 1.4 ohms. So this circuit can be replaced as a single battery which is in parallel with another battery, and here we have the voltmeter. So this is 5 volts, this is 0.2 ohms, and it is 35 volts, and this resistance is 1.4 ohms. Now this is a combination, two batteries in parallel combination, right? So these are batteries in parallel, but their polarities are opposite. Here we have negative positive, here we have positive negative. So in this case, E equivalent will be given as E1 by R1 minus E2 by R2 divided by 1 by R1 plus 1 by R2. So I'm assuming that the effective cell will be having polarity same as the polarity of EMF 35 volts. So E1 will be 35, E2 will be 5, R1 is 1.4 ohms, and R2 will be 0.2 ohms. So let us put the values. So 35 upon 1.4 minus 5 upon 0.2 upon 1.1.4 plus 1 upon 0.2. So that will be 0.2 and this will be 5. So it comes out to be 0. So we can say this combination, it is behaving like a battery which is having an EMF of 0 volt. If we have a battery of 0 volt, then there will be no current in the circuit and there will be no potential drop across the voltmeter. So it will show 0 reading. So the answer will be option 3. So there is no need to find the equivalent resistance. It does not help. It is not required, right, to find the effective internal resistance also. So option 3 is the right answer. Now let us see this question. the value of current in 6 ohms resistance. Right, so if you look at this, if this point is A and this point is B, so between A and B there are two real cells connected. So these are two real cells. Now here we can use E equivalent formula for cells in parallel, and they have the same polarity, positive negative positive negative. So E equivalent will be E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2. So this will give us 7, this will give us 14, no sorry 18, so this will become 25, and 6 by 4, it will be 5 by 25, 20 sorry 5 by 20, so it will be 25 by 5 times 20, so it comes out to be 100. So A equivalent will be 100 volt, and 1 by R equivalent will be 1 by 20 plus 1 by 5. So that comes out to be 5 by 20, that is 1 by 4. So R equivalent will be 4 ohms. So the equivalent circuit will look like this. So we have a cell of EMF 100 volt, and the internal resistance is 4 ohms, and it is connected with 6 ohms resistor. Now we can find the current in this circuit by using Ohm's law. So I will be V by total resistance. Total resistance will be 10, 4 plus 6 will be 10, so it will be 10 ampere. Now we know the current, and that what we have to find. So the answer will be option 3, right? Now let us see this case. In the given figure, the value of V0 will be, so if this is V0, let us take this voltage as 0. Here I'm taking it as 0 because we have connected this with the ground. So if this is 0, then at this particular point the voltage will be 2 volts, here it will be 4 volts, here it will be 6 volts, right? And we have to find V0. So what we can do in this case, or you can say if here we have the current I1, here it is I2, here it is I3, then I1 plus I2 plus I3 should be 0, right? Got it? It should be 0. So if that is the case, what is I1? I1 can be written as 2 minus V0, that is the potential difference, V by R, and resistance is 1 kilo. And I2 can be written as 4 minus V0 divided by 1 kilo. And I3 can be written as 6 minus V0 divided by 1 kilo, and that should be equals to 0. So from this, 2 plus 4 plus 6 minus 3 V0 should be 0. So it will be 12 by 3 equals to V0. So it will be 4 volts. So V0 comes out to be 4 volts. So this is one of the technique. So the same problem can also be solved by using the concept of cells in parallel. So if you look at these three, so these are three real cells which are connected in parallel. So if we show the equivalent EMF, so that will be E1 by R1 plus E2 by R2 plus E3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. And if the polarity is also same, right? So they have the same polarity because their positives are connected together. So this comes out to be 2 plus 4 plus 6 divided by 1 kilo divided by 3 by 1 kilo. So 1 kilo will get cancelled out. So 12 by 3, so this comes out to be 4 volts. And R equivalent will be nothing but 1 by 3 kilo ohms. So this arrangement can be shown with this circuit, a single battery and here we have V naught, and this is 1 by 3 kilo ohms, and it is 4 volts. Now we have this given, this arrangement is given, and it is not supplying any current. So the potential drop across this battery will be V naught minus 0, which is nothing but the EMF, and EMF is 4 volts. So 4 is the answer of this question. Right, so now let us see the next problem type, and it is based on half deflection method. So it is a experimental setup that we use to find resistance of a galvanometer. So let us see the setup, and then we'll see the numerical based on this concept. Suppose we have given a galvanometer and we want to find the resistance, and let us say G is the resistance of this galvanometer, and we have connected it with a DC source, and there is a high resistor connected in series with the DC source. Let us say this is R and this is E, and this R is very large in comparison to G. So what is the current supplied? So let me call this as IG1. So IG1 will be E divided by total resistance R plus G. Since R is very large, this can be written as E upon G. Now what we do, we'll connect a shunt in parallel to the galvanometer. So there is a shunt S, and we have the same setup, and this will be E. Let us say now this current is I, and in the galvanometer the current is IG2, and in the shunt it will be I minus IG2. So first of all, let us find what is this current supplied by the battery. So I can be written as E divided by total resistance. S and G are in parallel, so we can say SG upon S plus G plus R. That will be the total resistance. Again, since R is very large in comparison to G, and SG upon S plus G value will be less than G, so we can say in the denominator can be written as R only. So E upon R, because R is very large in comparison to SG upon S plus G. Okay, so now if if you look at the shunt and the galvanometer, they are connected in parallel. So we can say by Ohm's law, I minus IG2 times S should be equals to IG2 times G. Now from this, IS can be written as S plus G times IG2. Now what is this I? I is nothing but IG1. Can you see? This is IG1 and this is I. They are equal. So I can be written as E by R times S, S plus G, and IG2 as it is, right? So in half deflection method means the deflection in the galvanometer becomes half. So and we know that in case of a galvanometer, the deflection is proportional to the current in the galvanometer. So IG2 or IG1, they are proportional to the deflection. So if the deflection is getting half, the current will also get half. So we can say in case of half deflection, IG2 will be IG1 by 2. And IG1 is nothing but E by G. So let us write this: E by R times S is equals to S plus G, and IG2 can be written as IG1 divided by 2, or it can be written as S plus G times E by 2R. So by simplifying this, E by R will get cancelled out, and S upon S plus G can be written as 1 by 2. Clear? So this relation you can remember to find the internal resistance, not internal resistance, resistance of the galvanometer. Suppose if they talk about the 1/3 deflection method, in that case you can replace this 2 with 3, or you can remember a general formula: S upon S plus G is equals to 1 by X, where X can be, like, if it is 1/3 deflection, then X will be 3. If it is 1/4 deflection, X will become 4, and if it is half deflection, X will be equals to 2. Right, so now let us see a question. A teacher in his physics lab allotted an experiment to determine the resistance G of the galvanometer. Student took the observation for 1/3 deflection in the galvanometer. Which of the following is true for measuring the value of G? So we know that if you look at the result, it is S upon S plus G is equals to 1 by 3 in case of 1/3 deflection. So 3S is equals to S plus G, or G comes out to be 2 times S. So 1/3 deflection method can't be used to determine the resistance of the galvanometer. So option A is incorrect. 1/3 deflection method can be used, and in this case G equals to twice the value of the shunt resistance, and that what we are getting, G comes out to be 2 times S. So option B is the right answer. Now let us see the next question. A current of 200 microampere deflects the coil of the moving coil galvanometer through 60 degrees. The current to cause deflection through pi by 10 radian is, and we know that deflection is proportional to the current. So we can say theta 2 by theta 1 will be equals to I2 by I1. So theta 2 is given as pi by 10, and theta 1 is 60 degrees, which is pi by 3 in radians. And I2 we have to calculate, and I1 is given as 200 microampere. So pi will get cancelled out. So this will be 3 by 10 times 200 microampere. So this comes out to be 60 microampere. So I2 will be 60 microampere. So option 3 is the right answer. Let us see another question. The deflection in moving coil galvanometer falls from 25 divisions to 5 divisions when the shunt of 24 ohms is applied. The resistance of the galvanometer coil will be. So if you look at the deflection from 25 it becomes 5, so or you can say the deflection has reduced by a factor of 5. So we can say S upon S plus G will be equals to 1 by 5, and we have to find the resistance of the galvanometer. So S plus G is equals to 5 times S. So G comes out to be 4 times S, and S is given as 24. So 4 times 24 will be 96 ohms. So option 2 is the right answer. Now let us see this question. In the experiment to determine the galvanometer resistance by half deflection method, the plot of 1 by theta versus resistance of the resistance box is shown in the figure. The figure of merit of the galvanometer is 10 raised to power minus 1 ampere per division. So what is figure of merit? If you look at the dimension or the unit, it is ampere per division, where on the y-axis we have given 1 by theta, which is reciprocal of the division, right? So what we can do, so here we have given EMF, right? And V is equals to IR. So we can find the current, which is 2 by R, right? So this will be the relation between current and the resistance. Now if you look at this graph, if you find the slope, that will give us 1 by theta R, right? That because it will be dy by dx. So dy in this case will be 1 by theta, and dx will be R. And if you take any 2 points, if let us take this point and this point, let us find the slope. So dy will be 2 minus 1, and dx will be 6 minus 2. So it comes out to be 2 minus 1 upon 6 minus 2, which will be 1 by 4. So 1 by theta R comes out to be 1 by 4, and 1 by R is equals to I by 2. So it can be written as I by 2 times theta, that will be 1 by 4, and we have to find I by theta, so which will be 1 by 2. So it is 0.5 ampere per division, or we can write this as 5 into 10 raised to power minus 1 ampere per division. So if you look at the option, or option is not given, it's we have to fill the blank, so it comes out to be 5. So 5 is the answer of this question. Now let us see the next problem time, and it is based off the conversion of galvanometer into ammeter and voltmeter. Right, a galvanometer has a resistance of 50 ohms and it allows maximum current of 5 milliampere. So maximum current is nothing but the full scale deflection current. So Ig is 5 milliampere and G value is 50 ohms. It can be converted into voltmeter to measure up to 100 volt by connecting in series a resistance of resistance. So we have to find the resistance that we have to connect in series with the galvanometer to convert it into a voltmeter. So so the circuit will look like this. So we have a galvanometer and we are connecting a very high resistor in series, and across this combination the voltage drop comes out to be 100 volts. That is the maximum voltage this voltmeter can measure. So this is our voltmeter. So when we have maximum deflection, the current will be full scale deflection current. So this current will be Ig. So we can say 100 will be equals to I times G plus R by using Ohm's law. Ig is given, G value is given, we can find R. So 100 divided by Ig, which is 5 milli. So we have 1000 in the numerator minus 50. So that will give us R. So this comes out to be 20,000 minus 50. So it will be 19,950. So option 3 is the right answer. Let us see next question. A galvanometer has a coil of resistance 200 ohms. So G, this is G. With a full scale deflection current is 220 microampere. So that is Ig. The value of the resistance to be added to use it as an ammeter. So we want to form an ammeter which can measure from 0 to 20 milliampere. So when it is measuring 20 milliampere, at that instant the current in the galvanometer will be full scale deflection current. So the circuit in this case will be a galvanometer is connected with a shunt, and this shunt we have to calculate, and G value is 200 ohms, and we want to suppose if the current that this ammeter is measuring is 20 milliampere, at that instant we'll have full scale deflection in the galvanometer. So this current will be 20 microampere, and here we have 20 milli minus 20 micro, right? Now 20 milli is very large in comparison to 20 micro, so we can ignore 20 micro in comparison to 20 milli. So we can say 20 milli times S will be equals to 20 micro times 200. I have just equated the voltage across the shunt and the galvanometer. So 20 will get cancelled out, and this micro and this milli will give us 10 raised to power 3 on the left hand side. So shunt comes out to be 0.2 ohms. So option 2 is the right answer. Now let us see the next problem type, which is based on Ohm's law experiment. So let us see some illustration. So here we have given we have to determine the resistance R of a wire. A circuit is designed below, and the VI characteristic curve for this circuit is plotted for the voltmeter, and the ammeter reading are as shown in the figure. So we have to find the value of R. So we have to find this R, and we are measuring the current in the circuit in milliampere, and we are also measuring the potential drop across the resistor capital R, and this capital R is connected with 10 kilo ohms in parallel. So if you look at the graph I versus V, so with this graph, this voltage is across the resistor capital R, but the current is through both the resistors, right? So here I'm treating voltmeter as ideal. So voltmeter is ideal. So if this is the current which is being measured by the ammeter, so it is nothing but the sum of these two currents, I1 and I2, and we have to find the value of R. So resistance will be reading of the voltmeter divided by I2. So that should be the value of R. But if you go by this graph, it will give you the equivalent resistance of 10 kilo NR. So we can say it will be 10 kilo times R upon R plus 10 kilo, that will be V upon I, where I is the current reading shown by the ammeter. Okay, so let us find the ratio of I and V. So I'm taking these 2 points. So this delta I comes out to be 4 minus 2 milliampere, and delta V comes out to be 8 minus 4 volts. So we can write this as delta V upon delta I. So delta V is 8 minus 4 and delta I is 4 minus 2 milliampere. So this is 2, this is 4, so this comes out to be 2, so it comes out to be 2 kilo. So, and which is equals to 10k times R divided by R plus 10k. So let us remove this kilo, and this will give us 5 here. So 5R is equals to R plus 10k, or 4R is equals to 10k, or R comes out to be 2.5 kilo, or we can say 2500 ohms. So the value of resistance R is 2500. So that is the answer of this question. Now let us see another illustration. The variation of applied potential and current flowing through a given wire is shown in the figure. The length of the wire is 31.4 centimeter. So if you look at 31.4, it is nothing but 10 pi centimeter. The diameter of the wire is 2.4 centimeter. So diameter is 2.4 centimeter. The resistivity of the given wire is measured as x times 10 raised to the minus 3 ohms centimeter. The value of x is, and we have given the graph of potential and the current, right? So if I want to find the resistance, so resistance will be given as V by I. And in this case, V by I is nothing but the slope of this curve, which will be 1045. And it comes out to be 1. So 1 ohms is the resistance. And resistance is given as resistivity times length upon area of cross section. So that is 1. And resistivity is given as x into 10 raised per minus 3. It is in ohms centimeter. Length is given as 10 pi centimeter, whereas area of cross section will be pi 2.4 square by 4, right? Pi d square by 4, that is the area of cross section. So this comes out to be 1, and we have to find the value of x. So x will be, so let us remove this pi. So it comes out to be 2.4 times 2.4 by 4 divided by 10 raised per minus 2, so it will be 0.6, and it will be 1.44 times 10 raised per 2, which is 144. So x comes out to be 144. So that is the answer of this question. Now let us see the next problem type, which is based on the distribution of current. So let us see this illustration. In the given circuit, the current flowing through the resistance 20 ohms is 0.3. So through this resistor, the current is 0.3 ampere, while the ammeter reads 0.9. So, and here the current is 0.9 ampere, and the value of R1. So we have to find the value of this resistance. Okay, and this R1, 20 ohms and 15 ohms, they are connected in parallel, so they must be having the same potential difference. So let us find the potential difference across 20 ohms. Let me call this as V. So this V comes out to be IR, 0.3 times 20, so it will be 6 volts. So the same potential drop will be across 15 ohms. So here across 15 ohms we have 6 volts, across R1 we have 6 volts. So what is the current in 15 ohms resistor? And this current will be 6 by 15, so that will be 2, and this will be 5, so it comes out to be 0.4. So this will be 0.4 ampere. And by junction law, if this is 0.3, this is 0.4, it has to be 0.2, such that the sum of these three currents should be equals to 0.9. Now we know the current through R1. So we can say 6 is equals to 0.2 times R1, and R1 comes out to be 30 ohms, right? So 30 is the answer of this question. Now let us see this question. In the given circuit, the current in the resistor R3, so this is R3, this is R1, this is R2, and this is R4. So we have to find the current through R3. So in such type of a question, first of all, you have to find the current supplied by the battery. So for that, we have to find the equivalent resistance of this network. Now this 4 ohms and this 4 ohms are in parallel, so it will become 2 ohms. Now 2 ohms and these 2 ohms and 1 ohms are in series, so our equivalent comes out to be 2 plus 1, which will be 5 ohms. So the current supplied by the battery will be 10, that is the EMF, divided by the R equivalent. So it comes out to be 2 ampere. Now we have the current, so 2 ampere current is coming. Now it will split up into equal parts because both the branches have equal resistance. So that will be 1 ampere and this is 1 ampere. So the current through R3 is 1 ampere. So option 1 is the right answer. Now let us see this question. So we have to find the current flowing through R2. Now this is R2. Again, since we want to find the current in a particular branch, first of all, we have to find what is the current supplied by the battery. So for that, we have to find the equivalent resistance of this circuit. So let us do that. Now this 4 ohms and this 2 ohm, they are in series. So these two resistors are in series and it will become 6. Now this 6 ohms and this 6 ohms, they are in parallel. So it will become 3 ohms. Now this 3 ohm and this 3 ohm are in series. So it will become 6 ohms. Now this 6 ohms and this 3 ohms are in parallel. So it will become 6 times 3 divided by 6 plus 3. So which will be 18 by 9. So it will be 2 ohms. Now this 2 ohm and this 2 ohm are in series. So then it will become 4 ohms. Now this 4 ohms and this 4 ohms are in parallel. So this will become 2 ohms. So the R equivalent will be 2 ohms. So the current supplied by the battery will be 8, that is the EMF, divided by the equivalent resistance. So it will be 4 ampere. Now let us divide the current. So here we have 4 ampere and we know that this 4 and this 4 are in parallel. So the current will divide equally. So here we'll be having 2 ampere, here we'll be having 2 ampere. Now this 2 ampere will divide between 6 and 3, right? So here we have 3 and in and this resistor and this is nothing but 6 ohms, right? So let me show it here. If this is D and this is A and here we have 6 ohms and here the current coming is 2 ampere. So the current in 6 ohms will be what? Since these two resistors are in parallel, so the branch which will be having less resistance will be having more current. So we can say this current will be 2 times 3 divided by 3 plus 6, right? So I have divided the current in the inverse ratio of the resistance. So it comes out to be 3 by 9, so 1 by 3, so it will be 2 by 3 ampere. Now we got the resistance in this branch, so that will be 2 by 3 ampere. Now this current will divide equally in these two branches. So the current through R2 will be half of 2 by 3, that will be 1 by 1/3. So 1/3 ampere. So option 4 is the right answer. So I hope this concept is clear. Now let us see the next problem type, and it is based on the application of Kirchhoff's law. So there are two laws, Kirchhoff's junction law and Kirchhoff's voltage law. Let us see the application. Two resistance of 100 ohms and 200 ohms are connected in series with a battery of 4 volts. So there are two resistors, 100 ohms and 200 ohms, and they are connected with a battery, ideal battery, because it has zero internal resistance. So this is 4 volts. A voltmeter is used to measure the voltage across 100 ohms resistor, and we are using a voltmeter across 100 ohms, which will gives a reading of 1 volt. So the reading of this voltmeter is 1 volt, so we can say across this 100 ohm the voltage drop will be 1 volt. The resistance of the voltmeter must be, so let us take the resistance of the voltmeter as R. So we can treat voltmeter just like a resistor. So the equivalent circuit will look like this. So we have a resistor R which is connected in parallel with 100 ohms, and there is 200 ohms here, and this is the battery. So if this is 1 volt, then across 200 the potential drop will be 3 volt. 1 plus 3 is 4, that is the EMF of the battery. So from 200 volt, from 200 ohms we can find the current in the circuit. So let us do that. So the current I will be V by R. So it will be 1.5 into 10 raised to power minus 2 ampere. So that is the current. And the same current is being flowing through these two resistors, right? So this is I. So this I is nothing but V by R. Now R equivalent for this parallel combination will be 100 R upon 100 plus R, right? Okay, so let us simplify this. So 100 R upon 100 plus R is equals to 100 by 1.5. So this 100 will get cancelled out. So 1.5 R is equals to 100 plus R, so which will be 0.5 R equals to 100. So R comes out to be 200 ohms, right? So 200 is the answer. Let's see this question. Two cells are connected in opposition as shown. So it is negative positive, it is positive negative. So they are opposing each other. Cell E1 is 8 volt EMF and 2 ohms internal resistance. So it is 8 volt and 2 ohms, and the cell E2 has a EMF 2 volts and the internal resistance is 4 ohms. Now we have to find the terminal potential difference across E2. Right, so first step would be, let us find the current in the circuit. So let us assume the direction of the current. Let us say I is the direction of the current. So if you apply KVL in anti-clockwise direction, as we go from negative to positive, there is a increase in potential by 8, and we are going in the direction of the current through the resistor, so there will be a decrease in potential, so minus I times 2. Then now we are going from the positive to negative, so there will be a decrease in potential across this cell, so it will be minus 2, and since we are going in the direction of the resistance, in the direction of the current across the resistor, it will be minus I times 4, so it comes out to be 0. So here I have applied Kirchhoff's loop rule, and from this 6I comes out to be 6, so I will be 1 ampere. And we have to find the terminal potential difference across E2. So there is a current 1 ampere which is entering the positive terminal of the battery. So the terminal voltage in this case will be E plus IR. So E is 2 volts plus I current is 1 ampere and the internal resistance is 4 ampere. So this comes out to be 6 volts. So the potential drop across E2 is 6 volts. So that is the answer. Now let us see next question. In the given figure, R1, R2, R3 and R4, their values are given, right? 10 ohms, 8 ohms, 4 ohms, 8 ohms. Battery is ideal with the EMF 12 volts, equivalent resistance of the cell circuit and the current supplied by the battery. Okay, so if you consider these three resistors, their ends are joined together, right? So we can say R2, R3 and R4 are in parallel. So R2, R3 and R4, they are in parallel, so their equivalent will be 1 by 8 plus 1 by 4 plus 1 by 8. Let me call this as R prime. So this will be 1 plus 2 plus 1. So R prime comes out to be 2 ohms. Now this 2 ohms resistor is in series with R1. So R equivalent will be 2 plus 10. So 12 ohms is the equivalent resistance. So option 1 and option 3 are incorrect. And we want to find the current supplied by the battery. So current will be EMF divided by the equivalent resistance, which is 12. So it comes out to be 1 ampere. So option 2 is the right answer. Okay, let us see next question. 12 wires each having resistance 2 ohms are joined to form a cube. A battery of 6 volt EMF is joined across point A and C, and we have to find the potential difference between E and F, so between these 2 points. So if you look at the this circuit, let us see the symmetry. So what we can say by symmetry, and I'm considering this particular plane A, C, F, H. So by symmetry, B and D, they are equipotential. So let me call this as 1 and this is also 1. And E and G are equipotential. Let me call this as 2 and this is also 2. Now we have equipotential point. If we join equipotential point, it does not change the circuit. So let us join B to D and E to G, right? So when we do that, the resistor which is connected between AB and AD, they will become parallel, and the resistor which is connected between BC and uh, DC, they will become parallel, and the resistor connecting between BE and DG, they will become parallel. Similarly, this will become parallel to this, and this resistor will become parallel to this. Let me draw the circuit. So we can say this is A, here we have BD, and here we have C, here we have EG, and this will be H, and here we have F. So here we have two resistors which are in parallel. Here we have two resistors which are in parallel. Here we have two resistor in parallel. Two resistor in parallel, right? And all the resistors are identical. Here we have single resistor. Now if you and we are supplying, so current is entering from this end and it is leaving this end, right? So that is given to us. This is 6 volt battery. Now if you look at this circuit, we have to find the potential difference between E and F. Between E and F, okay? Let us simplify this. Look at these three resistors and these three resistors, right? So these two resistors are identical, right? So we can say this is 2, this is 2, 2. So 2 and 2 which are in parallel becomes 1, so 3. So this is 3 ohms. This is also 3 ohms. And these two will be 1. And this is also 1, right? So can we say we have a balanced Wheatstone bridge? Since it's a balanced Wheatstone bridge, we can remove this middle resistors, because the potential of BD will be same as the potential of EG in case of balanced Wheatstone bridge. So we can remove this resistor connecting between these two equipotential terminals. Now the simplified circuit will look like this. So we have 1 ohms, this is BD, then 1 ohms, C, A, and here we have 3 ohms, and this is EG, and here we have 1 ohm, and this so this will be 2 ohms and this will be 1 ohm, right? And this point is F, and there is a battery connected between A and C, 6 volt. Now first step would be, let us find the current supplied by the battery. Now this 3 ohms and 1 ohm, this 3 plus 3, they are in series, so it will be 6 ohms and this will be 2 ohms. So 2 and 6 are in parallel. So 2 times 6 divided by 2 plus 6, so it comes out to be 12 by 8, which will be 3 by 2. So that is the equivalent resistance. So the current will be, current supplied by the battery will be V, that is the EMF divided by the equivalent resistance, so 3 by 2. So it comes out to be 4 ampere. So 4 ampere current is coming. Now this branch has 2 ohms resistance and the bottom branch will be having 6 ohms resistance. So we can say this current I1 will be, so the resistance in these two branches is in 1:3. So we can say in the bottom branch it will be 3/4. Sorry, it will be 4 times 2 upon 2 plus 6. Got it? 2 upon 2 plus 6. So it comes out to be 8 upon 8, which is 1 ampere. Now the current in the bottom branch is 1 ampere. So between E and F, the current is 1 ampere. So the potential drop between E and F will be 1 volt, right? Because the resistance is 1 ohms. So it should be 1 volt. Okay, so a bit of lengthy question, but still doable question in JEE. Right, so let us see the next question. In a given figure, an ammeter A consists of a 240 ohms coil connected in parallel to a 100 ohms shunt. So this ammeter is nothing but a coil which is having a shunt of 10 ohms resistance, and this will be 240. Okay, so what we can say, the resistance of the ammeter will be 10 times 240 upon 10 plus 240. So it will be 2400 divided by 250, and it comes out to be 5 and 48, so it will be 9.6 ohms. So 9.6 ohms is the resistance of the ammeter, and we have to find the reading, so we have to find the current. So let us apply KVL in this loop. So the current will be 24 is the EMF divided by the total resistance of the circuit, which is 140.4 plus 9.6. So it will be 24 divided by 150, and we have to find answer in milliampere. So 10 raised to power minus 3 times 10 raised to power 3, and it will be 5 and 800. So it will be 160 into 10 raised to power minus 3 ampere. So the answer will be 160 milliampere. So 160 is the answer of this question, right? Now let us see the next problem. In the given circuit, the terminal potential difference of the cell. So we have to find the potential difference between A and B. So first step would be, let us find what is the current supplied by the battery. Now these two resistors are in parallel, so the R equivalent will become 2 ohms. So so the equivalent circuit will look like this. So there are two resistors. This is 1 ohm, this is 2 ohms, and the EMF is 3 volt. So the current will be EMF divided by the total resistance of the circuit, which is 1 plus 2. So it is 1 ampere. Now the battery is supplying a current of 1 ampere. So the terminal voltage will be E minus IR. E is 3 minus I is 1, and the internal resistance of the battery is 1 ohms. So it comes out to be 3 minus 1, which will be 2 volts. So option 1 is the right answer. Now let us see this question. The current flowing through 1 ohms resistor, which is connecting between A and C, is n by 10. The value of n is, right. So it looks like a Wheatstone bridge, but instead of a galvanometer we have a battery, a real battery, right? So we cannot simply remove this battery in this case, because this battery will going to maintain some potential difference between A and C. So it is not a case of a balanced Wheatstone bridge. So we cannot apply that concept. Okay. So what we can do, since we have to find the current through 1 ohms resistor, let us consider nodal voltages, right? So I'm assuming the voltage at D is 0 volts. So if it is 0, then the voltage at B will be what? It will be 5 volts, because between B and D there is a battery of 5 volts connected. So this will be 5. So if this is 5 volt, let us take potential at A as V1 and potential at C as V2. And the potential at this particular point will be what? It will be, at this point, it will be V1 minus 10. Is it clear? Because it's a 10 volt battery. Now if we consider junction A, so if I consider junction A, so we can say there is a current which is going in this direction, there is a current which is going in this direction, there is a current which is going in this direction. If this is I1, this is I2, and this is I3, then I1 plus I2 plus I3 should be 0 by junction law. And what is I1? I1 can be written as V1 minus 5 divided by 4, and I2 will be potential difference across 1 ohms resistor, which will be V1 minus 10 minus V2 divided by 1 ohms, and I3 is V1 minus 0 divided by 4. Now let us multiply this equation by 4. So this will become V1 minus 5 plus 4 times V1 minus 40 minus 4 times V2 plus V1 equals to 0, and it will give us 6V1 minus 4V2 equals to 45. So that is the first equation. And now apply Kirchhoff's junction law at C. So what we can say, so let us say there is a current in this direction, there is a current in this direction, there is a current in this direction, and the sum of these three currents will be 0. So we can say V2 minus 5 by 2 plus V2 minus V1 minus 10 by 1 plus V2 minus 0 by 2 should be 0. Now let us multiply this equation with 2. So we'll get V2 minus 5 plus 2 times V2 minus 2 V1 plus 20 plus V2 equals to 0. Now from this we will get 4 times V2 minus 2 V1 plus 15 equals to 0. Right? Now that is the second equation. Now if we add these two equations, 1 plus 2, if we add them, 4V2 will get eliminated. So we'll get 4 times V1 equals to 45 minus 15. So V1 comes out to be 30 by 4, which is 7.5 volts. So V1 is 7.5. And from the second equation, 4 times V2 will be 2 times 7.5 minus 15, which comes out to be 0. So V2 comes out to be 0. Now V2 is 0, potential and V1 is 7.5. So if you consider this 1 ohm resistor, to the right of this 1 ohm resistor at C the potential is 0, and to the left of this resistor the potential is V1 minus 10. So V1 is 7.5, so it will be minus 2.5, and the resistance is 1 ohms. So if you want to find the current, so current will be in the left direction, so it will be 2.5 is the potential difference divided by the resistance, that will be the current. So it will be 2.5 ampere and it is given as n by 10. So n comes out to be 25. So answer is 25. Not an easy question, but this is the way to solve such questions to avoid cumbersome KVL equations, right? Now let us see the next problem type, and it is based on instrument, and the first instrument we're going to discuss is meter bridge. The resistance per centimeter of a meter bridge wire is R, and with X ohms resistance in left gap. Balancing length from the left end is 40 centimeter with resistance with 25 ohms resistance in the right gap. Now the wire is replaced by another wire of 2R resistance per centimeter. The new balancing length for the same setting will be, right, since we are not changing the length of the wire, if you change the resistance per unit length for the wire, there will be no change in the balancing length. So it will remain same as 40 centimeter. So option 4 is the right answer. Let us see next question. In a meter bridge, when a resistance in the left gap is 2 ohms, let me just show. Resistor in the left gap is 2 ohms and the unknown resistor, and here we have unknown resistor, let us say R. The balance length comes out to be 40 centimeter. So there is a galvanometer and here we are getting balance length, and this length is 40 centimeter, and there is a driver's battery which is setting some current in this circuit. On shunting the unknown resistor with 2 ohms, so this is the unknown. Now we are shunting this R with 2 ohms. The balance length changes by, so let us see what happens. If we shunt this with 2 ohms, let us say the balance length becomes L, and this will become 100 minus L, right? Because it's a meter bridge, it's a meter wire, meter long wire, and L is in centimeters. So before shunting the unknown resistor, the equation will be for the balanced Wheatstone bridge, it will be 2 by 40 equals to R by 60, right? And later on it will become 2 by L equals to the equivalent of R and 2, which are in parallel, will be 2 times R upon 2 plus R divided by 100 minus L. Now from the first equation we can find the value of unknown resistor. So this will be 20, so this will give us 3, so R comes out to be 3 ohms. Now let us substitute R as 3 ohms in the second equation. So 2 by L is equals to 6 upon 5, and we have 100 minus L in the denominator, so this will give us 3. So 500 minus 5L is equals to 3L, and from this 8L comes out to be 500. So L will be 62.5 centimeter. So the new so this is the new balance length, but we have to find the change in the balance length. It was 40 initially, now it is 62.5, so the change will be 22.5 centimeter. So option 1 is the right answer. Let us see the next question. A wire of length 10 centimeter and radius root 7 into 10 raised per minus 4 meter connected across the right gap of a meter bridge. So we have given when a resistor 4.5 is connected in the left gap, so there is a resistor of 4.5 in the left gap, and there is a wire which is having a length 10 centimeter and its radius is root 7 into 10 raised per minus 4 meter. And there is a meter wire. The balance length is found to be at 60 centimeter from the left end. So there is a galvanometer, and here we have the balance length. So this is 60 centimeter. If this is 60, this will be 40. If the resistivity of the wire is R into 10 raised to power minus 7, the value of R is. Okay, so what is the resistance of this unknown wire? It will be resistivity, which is R into 10 raised to power minus 7, times length, which is 0.1, divided by the area of cross section, which will be pi R square, and it will be 7 times 10 raised to power minus 8. So this 10 raised to power minus 8 will get cancelled out with 10 raised to power minus 8 in the numerator. So that is the resistance. So let us apply the balanced Wheatstone bridge condition. So here there is a battery also, right? So 4.5 divided by 16 should be equals to R by 7 pi divided by 40. And 7 pi is what? If I take pi as 22 by 7, then 7 pi will be 22. So this will get cancelled out. It will give us 2. This will be 3. So it will be 9 by 3 equals to R by 22. So this will be 3. So R comes out to be 66 ohms. Not ohms. R value comes out to be 66. So option 3 is the right answer. Now let us see the next type of next instrument, that is Wheatstone bridge. Okay, so Wheatstone bridge principle is used to measure the specific resistance S1 of a given wire. Specific resistance is nothing but the resistivity of the wire. Having length L and radius R, if X is the resistance of the wire, the specific resistance will be given by this formula, X times pi R square by L. If the length of the wire gets doubled, then the value of specific resistance will be. Now specific resistance is the property of the material. So even if you change the length of the wire, it does not make any difference to the specific resistance because we are not changing the material. So it will remain same as S1 only, right? So option 4 is the right answer. Now let us see the next type of problem type. It is potentiometer. Potentiometer is not in the syllabus, but still in 2024 there was a question based on potentiometer. So that's why it is recommended you to cover this topic. Let us see. To measure the internal resistance of a battery, potentiometer is being used. For R equals to 10 ohms, the balance point is observed at L equals to 500 centimeter, and for R equals to 1 ohms, the balance point is observed at L equals to 400. The internal resistance of the battery is approximately. Okay, let me first draw the diagram here. Let's say this is the potentiometer wire, and this end is A and this end is B. And in case of potentiometer, we have a long wire. It can be a 5 meter, 10 meters long. And in the secondary circuit, we have a cell whose internal resistance that we need to calculate, right? So this is R and this is E, and there is a resistor of 10 ohms. So first I'm taking the case when we have 10 ohms in parallel to the battery, and there is a galvanometer, and we are getting a balance length which is 500 centimeter. Okay, so this is 500 centimeter, and in the primary circuit we have a battery. So when there is no deflection in the galvanometer, so whatever current is being supplied by the primary battery, this current will pass through the potentiometer wire. And the current supplied by the unknown cell, this current will keeps on circulating in this particular loop, right? But what we can say, if this point is J1, so we can say this point is also A and this point is also J1, right? So the potential, so the terminal voltage across the unknown cell will be same as the potential drop across the length AJ1 of the potentiometer wire. Okay, right. So let us see. If this current is I, so we can say VAJ1, and let us the potential gradient across the potentiometer wire is phi, so this will be phi times 500, right? And if you look at this circuit, and this current is says I, so this I can be written as E divided by 10 plus R. So the terminal voltage VAJ1 can be written as E minus IR, E upon 10 plus R times small r. Got it? And this comes out to be 10E upon 10 plus R. Clear? It will become 10E upon 10 plus R. So this is also equals to 10E upon 10 plus R. But suppose if we replace 10 ohms with 1 ohms, in that case the balancing length will change, right? So the same thing, let me call this as VAJ2. So 5 times 400 will be equals to 1 times E upon 1 plus R. I hope this is clear. That is for the second case. Now if you take the ratio of these two equations, so we'll get 5 by 4 equals to, E will get eliminated. So it will be 10 E upon 10 plus R times 1 plus R upon E. So E will get cancelled out. So this will give us 2 here. So 10 plus R is equals to 8 plus 8R. So 7, yes, this will be 7R comes out to be, so 7R comes out to be 2. So R will be 2 by 7, and which is nearly equals to 0.3 ohms. So we have to find the approximate answer. So option 2 is the right answer. Let us see the next question. A potentiometer wire of length 300 centimeter is connected in series with a resistance of 780 ohms and a standard cell of EMF 4 volt is there, right? A constant current flows through the potentiometer wire and the length of the null point for the cell of EMF 20 milliohms is found to be 60 centimeter. So in this case, whatever current which is being supplied by the primary battery, this current is passing through the potentiometer wire, and there is no current in the cell of EMF 20 millivolt. So we can say the voltage across AC, so VAC is nothing but 20 millivolts, right? And we have to find the resistance of the potentiometer wire. So what we can do, the length of the potentiometer wire is 300 centimeter, and let us say small r is the resistance per unit length. So resistance in ohms per centimeter, right? So we can say resistance of AC will be 60 times R, and the resistance of CB will be 240 times R, because the length of CB is 240. Now if you look at this loop, if I apply KVL in this loop, the total resistance of this loop will be 780 plus 60R plus 40R. And so the current, so this current I will be 4 divided by total resistance 780 plus 300R. And this current is passing through AC also. So we can say I will be VAC divided by the resistance of AC equals to 4 upon 780 plus 300R. So VAC is 20 milli and RAC is 60R. So 4 upon 780 plus 300R. So let us simplify this. So this will give us 3 here, and we have 10 raised to power minus 3 times 780 plus 300R equals to 12R. So this comes out to be 0.78 plus 0.3R equals to 12R. So 0.78 is equals to 11.7R. So R comes out to be 0.78 divided by 11.7. Now that is resistance per centimeter, and we want to find the resistance of the potentiometer wire. So if I multiply resistance per centimeter with the length of the wire, we'll get the resistance of the potentiometer wire. So the resistance will be 0.78 upon 11.7 times 300. So this comes out to be 24 to 234 divided by 11.7, and it comes out to be 20. So 20 ohms is the resistance of the potentiometer wire. So I hope this question is clear to you. Now let us see the next problem type, and it is based on joules heating. So let us see the first question. By what percentage will the illumination of the lamp decreases if the current drops by 20%? Illumination depends upon the power dissipation, right? So we have to see what happens to the power. So by what percentage will the illumination of the lamp decreases? So now current is decreasing by 20%. So current will become I minus 20% of I. So that comes out to be 0.8 I. So the new power will be I prime square times the resistance. I'm taking resistance is not changing. I prime is nothing but 0.8 I. So it will become 0.64 IR, I square R. Now this I square R is the original power dissipation. So we can say the new power will be 0.64 times the original power. Now how much is the change in the illumination? So that will be the percentage change in the power. So percentage change will be P minus 0.64 P, that is the change, divided by the original value times the 100. So this comes out to be 0.36 times 100. So that is 36%. So the illumination will decrease by 36%. So option 3 is the right answer. Let's see this question. When a potential difference V is applied across a wire of resistance R, it dissipates energy at a rate W. W is V square by R. If wire is cut into half and these halves are connected mutually parallel across the same source. So suppose this is the wire which is having a resistance R. So if I cut this into two parts, then both the parts will be having a resistance R by 2, because resistance is directly proportional to the length for a given cross section. So this is R by 2, this is R by 2. Now we are connecting these R by 2 and R by 2 in parallel. Okay. Now R by 2 and R by 2 are connected in parallel with a source of voltage V. Now in this case, this energy dissipation rate will be, so let us say W prime is the new dissipation rate. It will be V square divided by the resistance of this new combination, which will be R by 4. So which is nothing but 4 times the original power dissipation. So the option 4 is the right answer. Let us see the next question. In the following circuit, the battery has an EMF of 2 volts and the internal resistance is 2 by 3 ohms. The power consumption in the entire circuit is, okay, so first we have to simplify. Let us first find the R equivalent. So for that we have to identify the series and parallel combination. So if you consider these two resistors, they are in parallel, and similarly these two resistors are also in parallel because their ends are joined together. So this will be 1 ohm. This is also 1 ohm. So so the equivalent circuit will look like this. So there is a resistor of 2 ohms, and here we have 1 ohm, and this is 1 ohm, and this is 2 ohms, right? And there is a cell of EMF 2 volts, and there is a resistor 2 by 3 ohms. So this is nothing but a 3 2 ohms resistor connected in parallel. So this will be 2 by 3 ohms. So our equivalent of this circuit will be this 2 by 3 and this 2 by 3 are in series. So it will be 4 by 3 ohms. So the current supplied by the battery will be EMF divided by the total resistance. So it will be 3 by 2 ampere. Now we know the current and we know the R equivalent. So the power dissipation will be I square R equivalent. So I is 3 by 2, so 9 by 4. R equivalent is 4 by 3. So this will give us 3. 4 will get cancelled out, so that will be 3 watt. So 3 is the answer of this question. Right, so now let us see the next problem type, and it is based on bulbs. And let us see a typical question. An electric bulb rated 220 volt and 100 watt. So whenever we have given ratings, it is given to find the resistance of that bulb, right? So for example, for this particular bulb, the resistance R1 will be given as V square by P. So that will be 220 square upon 100. Similarly, and it is connected in series with another bulb, which is, and the resistance of the second bulb will be 220 square divided by 60. Now, if the voltage across the combination is 220 volt and the power consumed by 100 watt bulb will be about, so we have to find the power dissipation in the bulb of power 100 watt. So let us see. So this is say the first bulb which is connected in series with second bulb, and across these two bulb the voltage is 220 volts, and we want to find the power dissipation in the first bulb, right, which is having a resistance R1. So first of all, both the bulb will be having same current. If they are having same current, then we can say the potential will be divided proportional to the resistance. So we can say V1 will be equals to 220 times R1 upon R1 plus R2. So that is the potential across the first bulb. And if you want to find the power dissipation, so that will be V1 square divided by R1. So it comes out to be 220 square times R1 upon R1 plus R2 square. So let us put the values. So power dissipation will be 220 square times R1 is 220 square by 100, and in the denominator we have R1 plus R2, so it will become 1 by 100 plus 1 by 60 times 220 raised to power 4. Now this 220 raised to power 4 will get cancelled out, so we got power as 1 upon 100 times LCM will be 300, so 3 plus 5, so it comes out to be 300 upon 100 times 8. So it will be so it is square of that, right? Square of this. So 300 square, and then we have 8 square. This is 100. So let us simplify this. So 9 into 10 raised to power 4 divided by 64 into 10 raised to power 2. So which comes out to be 900 upon 64. So this will be 8, and this comes out to be 1, and then 1, 2.5. So this will be 14.06. So the answer will be close to 14 watt because it's an integer type question, so it is 14. Now that is the next question. An electric bulb rated 50 watt 200 volt is connected across a 100 volt supply. The power dissipation of the bulb is, so we have to find the power dissipation. So from this data we can find the resistance. So that will be 200 square upon 50. So it will be 4 into 10 raised to power 4 divided by 50. So it will be 0.8 into 10 raised to power 3. So it will be 800 ohms. And it is connected across 100 volts. So the power dissipation will be V square upon R. So it will be 100 upon 8, which comes out to be 12.5 watt. So option 2 is the right answer. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.